Yeah, I can hear you now. I will briefly introduce you and your professors. Will you allow me a couple of minutes? Can you hear us?
Oh.
Okay. Well, very briefly, I will mention that Wenmiao Li is a 4-year PhD candidate. He's working in molten salt electrolytes at Wuhan University. Professor Dihua Wang, who also is joining us today, he's a professor at Wuhan University. And Professor Huayi Yin also works at Wuhan University. So it is our great pleasure today to have this presentation from this very important group. Please, Wenmiao, go ahead.
Oh, okay. Hello, everyone. My name is Wenmiao Li, and I'm a PhD candidate from Wuhan University in China. I'm very pleased to be here to make a presentation for you. My supervisor, Professor Dihua Wang, and Professor Huayi Yin are in this room now. The topic of my presentation is that the phase evolution and mass transfer in lithium tin antimony battery during discharge. As we know that you are familiar with liquid metal battery, I will not introduce the principle of the liquid metal battery in this talk. In liquid metal batteries, the intermetallics with high melting point can always be found in the discharged positive electrodes, such as lithium antibalide, lithium bismuthide, and calcium bismuthide in different batteries. If the solid phase is appearing during discharge, there is no doubt that its growth in timing distribution and the physical and chemical properties have a significant impact on the battery performance. Our interest is about the solid phase and its effect on the thermodynamic and kinetic properties of the liquid metal batteries. So the first question is, how does the appearance of the solid intermetallics happen? To find the answer, we built an in-situ observation device to monitor the surface of liquid tin antimony alloy during discharge. The tin antimony alloy is the positive electrode of lithium tin antimony battery. There is a 3-electrode cell in this furnace. The working electrode is liquid tin antimony alloy, and a camera beyond this furnace to record the surface of the working electrode. The left is the video of the liquid tin antimony alloy during discharge, and the right is the discharge curve. We can say that the electrode is liquid at the beginning, and then the solid phase starts to grow on the surface. The surface has been covered now. There are pictures of the electrode surface with different discharge time. The solid phase starts to grow just at the point about 10% discharge dips. After 20% discharge dips, the solid phase has fully covered the surface of the liquid electrode, and the appearance of the solid phase just at the point when the potential starts entering the stable range. It's the video during discharge and the charge process and a larger current density. It's discharge process. the solid phase is growing. It's a charge process. The solid phase is converted to liquid state. Similarly, the potential went to a stable range when the solid phase appeared, and during charge, the solid compound disappeared. It shows that the solid phase has a good reversibility for its formation and breakdown, which is also the basic properties to be used as a secondary battery. The post-mortem analysis shows that the solid phase is the lithium antimalide. And the second question comes, why does the solid lithium antimalide generate during discharge? The binary metal battery is much easier to analyze because we have the phase diagram. For example, we first analyze the magnesium antimalide battery from the phase diagram. From the phase diagram, the magnesium antimalide, which has a high melting point, will be formed when the magnesium content reaches a certain value in the liquid magnesium antimalide alloy electrode. When the magnesium content reaches this same value, the magnesium antimalide is generated and the potential becomes stable. Therefore, in the cycle of thermodynamics, the formation of the solid phase is a spontaneous reaction. We can even accurately predict when the solid phase will be formed if the positive alloy is homogeneous. When the positive alloy is lithium tin antimony ternary alloy, the lithium preferentially react with antimony because the potential that lithium reacts with antimony is much higher than the reaction of lithium with tin. From lithium antimony phase diagram, the lithium antimalide will be formed if the lithium content increased. So the lithium antimalide is formed during discharge in lithium tin antimony battery, and the metal tin is used as an inert solvent. When does the solid lithium antimony occur? There is no lithium tin antimony ternary alloy phase diagram available to us. If we want to know the lithium content in the liquid alloy, which leads to the formation of lithium antimalide, we can only measure it. By coulombic titration test, the cover of the equilibrium potential and of the positive electrode with the lithium content is obtained. This point, which is the potential entering the plateau region, represents that the formation of the lithium antimalide. What is the effect of the lithium antimalide on the positive potential? Similarly, we first analyze the binary metal battery, the magnesium antimony battery. The discharge reaction is that the magnesium reacts with liquid magnesium antimony alloy to increase the magnesium content. From the reaction, gypsum free energy or next equation, when the alloy electrode is liquid, the positive potential is become lower with the increasing of magnesium content. After the magnesium content reaches the critical value, the potential remains unchanged because the subsequent reaction is the formation of the magnesium is the solid phase. The same reaction, the same gives free energy, which leads to a stable potential range. In lithium-tin antimony battery, the positive electrode is lithium-tin antimony ternary alloy. Its positive reaction is more complicated after the solid lithium antimony is formed. The potential goes to a stable range, but it still decreases slowly. The reason is that with the formation of the lithium antimonide, the concentration of the antimonide in the liquid alloy is decreasing. The active material decreases in positive electrode, which leads to the decreasing of the potential. From the view of the kinetics, there are two different mass transfer models before and after the formation of solid phase on the positive electrode. When the positive is liquid, the lithium ions are reduced on the surface and at the same time diffuse into the liquid alloy. The concentration of the lithium in the liquid alloy presents a surface to bottom gradient distribution at any discharge time. When the content of lithium on the surface of the electrode reaches the critical value, the solid lithium antimonide starts to grow and cover the surface. The lithium ions need to diffuse across the solid layer to be reduced and combine with the liquid alloy below the solid layer. So the battery capacity and rate performance are determined by the ionic conductivity of the solid layer. The ionic conductivity of lithium antimonide and lithium bismuthide were measured by Hutchins and Wapner. The two intermetallics have a high ionic conductivity, so the lithium-tin antimony and the lithium bismuth batteries have high capacity. All of the bismuth or antimony in positive electrode can be converted to lithium bismuthide or lithium antimonide. It's worth to point out that the lithium concentration at this interface will remain unchanged because this interface, this is a coexistence of the solid phase and the liquid phase. The appearance of the solid phase is controlled by the lithium concentration on the surface of liquid positive alloy. This concentration is determined by the current density and the diffusion rate of lithium. If we know the diffusion coefficient, we can predict when the solid phase appears during discharge. From the fixed law, if we know the relationship between the lithium concentration on the surface with time during discharge, the diffusion coefficient can be solved. However, during constant current electrolysis, we can only get the potential with time. So we want to build a bridge to connect the potential and the surface concentration. From the coulombic titration test, we can get the relationship between lithium content and the equilibrium potential, and then the curve in the liquid region was fitted to obtain the mathematical formula of the lithium concentration with equilibrium potential. In this way, we establish the relationship between the surface concentration and the equilibrium potential. It's a potential time curve during short constant current discharge. We know that the potential of the liquid lithium tin antimony alloy is determined by the lithium concentration on the surface. Therefore, from the formula of the lithium concentration with equilibrium potential, this potential time curve can be converted to surface concentration time curve. And then the diffusion coefficient can be solved from fixed second law. By this method, the diffusion coefficient of lithium in liquid alloy with different lithium concentration are obtained. Let's make a summary. The phase evolution is a positive electrode during discharge was in situ observed. We built a thermodynamic model to explain the influence of solid phase on battery voltage. There are two different mass transfer models before and after the appearance of solid phase. And then we built an electrochemical method to measure the diffusion coefficient of lithium in liquid alloy. The solid phase has such a great influence on the performance of the liquid metal battery, especially its growth may lead to the reduction of the distance between the positive and the negative electrodes, and even cause the battery to short circuit. So it's very important to monitor the solid layer growth process during discharge. Therefore, in this part, we attempt to investigate the generation and the growth process of the solid layer by numerical simulation. During discharge, there are two different mass transfer models in liquid region and liquid solid region. We proposed a two-step model to simulate the mass transfer and phase evolution in positive electrode during discharge. When the positive alloy is liquid state, the reduced lithium diffused into the liquid alloy. The lithium flux is constant during constant current discharge. We can use the constant flux diffusion model to simulate this mass transfer process. If the equilibrium voltage corresponding to the surface lithium concentration and various polarization are considered, we can also simulate the discharge curves. The green area is the formula about the equilibrium voltage with the lithium concentration on the surface of positive liquid alloy. This relationship was obtained by coulombic titration mentioned before. The constant flux diffusion model needs the diffusion coefficient of lithium in liquid lithium tin antimony alloy. These parameters have been measured before. Herein, the discrete diffusion coefficients with different lithium concentration were fitted to a formula which was used in simulation. The internal resistance of the battery was measured by EIS, and the electrochemical polarization is obtained by BV equation. The lithium concentration on the surface of positive liquid alloy was simulated under different discharge currents. The concentration can't exceed this value. It's the critical concentration we have measured. Beyond this value, the solid phase will be formed. The discharge covers under different current densities were also simulated, and they deviate the experimental curves very small. The effect of the thickness of positive electrode on the enrichment rate of lithium concentration on the surface is also simulated. The enrichment rate decreases with the thickness of the alloy. It's the distribution of lithium in the liquid positive electrode during discharge. The concentration presents a gradient distribution from surface to bottom. When it was discharged for 3,300 seconds, the surface concentration reaches the critical point, and we can find that the concentration gradient will still present. When the concentration reaches the critical value, the solid lithium intermetallic will be generated and cover the surface. After this point, the lithium ions need to go through the solid layer to be reduced at the interface of the solid layer and the liquid lithium tin intermediate alloy. The reduced lithium flux will be divided into two parts. One partial lithium flux continue to diffuse downward because the concentration gradient is still present. And the other partial is used to generate solid lithium intermetallic until the lithium concentration in the liquid alloy is uniform and reaches the critical value. What the lithium flux is used to form lithium intermetallic. If we know how much lithium flux for diffusion, the other flux is for forming lithium intermetallic, and the growth speed of the lithium intermetallic can be calculated. In this process, there is a key feature is that the lithium concentration at this interface is constant. It remains the critical concentration. So we can use a constant concentration diffusion model in liquid solid region. The black line is the lithium flux for diffusion, and the red line is the flux for lithium intermetallic. At the beginning of the discharge, the positive electrode is liquid. What the lithium flux diffuse into the alloy to increase the lithium concentration. When the solid phase is formed on the surface, one partial lithium flux continues to diffuse into the liquid alloy, and the other partial is to form lithium intermetallic until the lithium concentration in the liquid alloy is uniform and reaches the critical value. What the lithium flux is used to form lithium intermetallic, and then the solid phase growth rate can be obtained. And then the effect of the thickness of positive electrode on the growth of solid layer is also be simulated. As the positive electrode thickens, the later the solid phase appears, but the thickness of solid layer will increase proportionally. By the two-step model, we can monitor the mass transfer and phase evolution process during discharge. The solid phase has a significant influence on the capacity rate performance, even the safety operation of the liquid metal batteries. Maybe the two-step model is a little simple. Some factors are simplified, such as the convection, the current distribution on the positive surface, and so on. However, we think that the value of this two-step model is that it can describe the two different mass transfer process during discharge and link them together to a continuous process. And it's a summary of this, or it's a summary of this part. That's my presentation. Thank you. Thank you very much.